Welcome back to Code Meets World. Today we're looking at LeetCode number 347, which is top k frequent elements. In this problem, we're given an integer array called nums and an integer k, and we need to return the k most frequent elements, and we can return this in any order. So looking at the examples, in this array, with k equals 2, we need to return the 2 most frequently occurring elements in the array. So we can see that that's element 1, which occurs 3 times, and element 2, which occurs twice. So that's what we output as the solution. And down here, k is just 1, and there's only one value in the array, so we just output that. So at first glance, this problem looks pretty approachable, but I think there are 2 distinct things that we need to do here. The first of which is go through the entire input array and count the occurrences of every different value. And then second, we need to go through and pull out the k most frequently occurring terms. So basically count everything first. So I'll make that step 1. Step 1 is count. And then step 2 is find top k. So if they want just the most frequently occurring word, we'll return that. If they want the 10 most frequently occurring, we'll return that. So I'm going to talk about these one at a time. So first, the count. Anytime that I need to do counts, I'm always thinking about a dictionary. So this case is going to be no different, I think. So what we can do is we can loop through the entire input, and each time we get to a number, we can just add that to the dictionary, and then we increment the count each time we find something new. So what we'll end up with at the end is each distinct value that's in the array, and then the count of how many times we see that. So this is just showing that element 1 occurs 3 times, element 2 occurs twice, and element 3 occurs just 1 time. So I think that's the first step. Just iterate through the whole array and build these counts. Now I think finding the top k elements is a bit tricky, because if the task was just to find the top 1, the top 2, the top 3, if it stayed the same every time, we could simply have, for example, max 1 and max 2. Say we needed to find the top 2 things, and then we could just insert the first 2 elements here, and then we could just go through and compare to those values and just update them over time. But we can't do that here, and that's because the number of values we need to return is a variable. We don't know what it's going to be at the start of the problem. So if you watched some of my previous videos, which I'll link at the top of the screen right now, or you're familiar with heaps, I think that's actually going to be the secret to doing this efficiently. If you haven't seen or don't remember what heaps are, that's just basically a tree data structure where the smallest value is at the top, the root of the tree, and then all values below the root increase in value. So for instance, we could have a 1 at the top, a 2 here, a 7 here, we could have a 3 here and a 4, here we could have a 10 and a 50. The only requirement is that the children of a root have to be larger than it. So this is just one example of that. But what's really cool about heaps is that when you add something new or remove something, the heap automatically re-updates itself to maintain that heap property. So for instance, if I added a 12 to this heap, it would figure out that the best place for it to go would be perhaps over here. And it would just do that automatically. But if I inserted the value that needed to go up here, for instance, the heap would update itself to account for that. And when we remove something, we're always removing from the root And then the rest of the heap will update itself by moving the 2 up to the top, so that the heap maintains its property. So why am I telling you all of this? Well, I think what we can do is create a heap that is size k. And then so basically we have this dictionary first, then we create a heap of size k. And the reason that size k is that we'll start by adding k elements to it. So for example, the first 2. And then as we consider more values from this dictionary, we can see, hey, is the value that I'm considering now larger than the value at the top of the heap? And if that's the case, we can remove this value and add this value. So let me show you an example of what I mean by that. Using this dictionary here, I'm not going to do it in this order or it won't work as well. So we don't know what order we're going to get the keys when we're iterating through a dictionary. So let's say we're going to start at the bottom and move towards the top. How we can do this is say, okay, we're going to create a heap and we'll start by placing this bottom value in it. And a quick aside, this heap here, I just put integers in, but there's a really cool trick that we can use if we want to store more than one value in the heap. So for instance here, we want to store and keep track of the counts, but remember at the end of this problem, we need to return the actual number, not the count. So we need access to both of these values, and we can actually store both of those in a heap by using a tuple. A tuple is just a list with, for example, 2 elements in it. And if we insert a tuple into a heap, it will use the first value to heapify all the tuples. So it'll look at the first value and use that and keep the smallest one at the top. And so this is perfect for our use case because it'll keep the smallest count at the top if we put count here. And if we put the actual number here in y, we'll have all of our values in the heap, which is perfect. So back to what I was saying. We'll start by putting this 3, 1 into the heap. So then I would insert, again, we'll put the count first. So the count is 1 and the value is 3. We'll put that first. Next, we'll put 2, 2. Our heap is still too small because k is 2 and we want our heap to be as large as k. So we just add 2, 2 in the same way. And the value 2 is larger, so it would go as a child of the heap. And this would happen automatically when we add it. Now when we go to add the last value, we notice that the count is 3. And because the heap is already of size k, we need to check, okay, is this count larger than the count of the topmost value in the heap, which is the smallest? And it is. 3 is larger than 1. So what we need to do is remove the root. So we're just left with 2, 2. And then we add in the value that we just saw, which is 1, 3. And because 3 is larger than 2 in terms of the count, it would be a child, and we would get this. And now we're at the end of the dictionary, so we would just be able to look at our heap, which is this, and we could just extract, not the counts, but we could extract the 2 numbers that are associated with everything in the heap, and that would give us our solution of 2 and 1. The first step is, like we talked about, we're going to calculate this count dictionary. So I'll call it counts. I'll set that equal to an empty dictionary. And then I can iterate over each num in nums. And I can check, first of all, if num is in counts. If it's already there, then we can say counts num plus equals 1. So if we've already seen the value, we'll just increment its count by 1. 1. If we haven't seen it before, so an else, num is not in counts, we need to add it. So we can say counts num, and we can just set that equal to 1 because it's the first time that we're seeing it. So that's how we can build a very simple dictionary that counts the occurrences of everything. So what we'll be left with is counts will equal something that looks exactly like this. So that's perfect. Step 2 is finding the top k values. So like I mentioned, we need to create a heap. And another name for a heap is sometimes a priority queue. You might hear that. But I'm just going to call it heap, and I'll set it equal to an empty array, and then I can call heapify, which is a built-in Python function, and I can call that on heap. Again, go watch my 2 videos about heaps if this is unfamiliar to you, because I explained the syntax in that video. So once we have those, we need to loop over counts, and we need to start adding things to the heap. So I can say, and to loop over a dictionary, remember, we can say for, this would be num counts in, or not counts, I'll just call it count. In counts.items, which will give us the key value pair of everything in our dictionary. So for num counts in counts.items, the first thing we want to ask ourselves is if the length of the heap is less than k, because remember, we want our heap to be exactly size k, because we're going to be returning the k largest elements but based on count. So if the length of the heap is less than k, we simply just want to add whatever we have, whatever we're on right now, to the heap, just straight add it. So to do that, we can say heap push, again, another built-in function, heap push, and you have to say the name of the heap that you want to add it to. In our case, it's the heap variable, and then the value you want to add. And now this is the important part. Remember that we talked about, in this case, we need to add these tuples because we want to keep track of both the actual counts, which are going to get sorted, and then we also want to keep track of the number itself that's associated with it. So at the end, we can return those. So what I'm going to add is actually a tuple of first the counts. So we'll add count, and then second the num. And like I mentioned, count is what's going to be heapified and sorted from smallest to largest. So it's important that count goes first here. So that's our case if the length of the heap is less than k. If that's not true, we need to check if we need to replace the root or not. And the way we're going to do that is by checking if the new thing that we're adding is larger than the root. Because if it's larger, that means we need to replace the root and add the larger, because we want to keep track of the k largest counts. So to do that, we can say lf, and I have this wrong, lf, we want to check if count, because that's the one that we're on right now, lf count is greater than, and to get the first value in the heap, so the root, we can say heap 0, so this accesses the first value, the root, and then we want the count of it, which is the first value in the tuple. So we can access that kind of like it's an array and just say 0, 0. So this is going to get the root of the heap and the first value of that. And we want to check if our current count, so whatever count we're seeing in the dictionary value that we've looped over, if that's bigger than the root's value in the heap, that means we need to replace it. And what we could do to do this is a heap pop and then a heap push. So pop off the root and then push on the new value. But there's actually a way to do these both at the same time, which is a bit more efficient computationally. And that's by saying heap replace. And we have to give it the name of the heap. And then we have to give it the value that we want to add on, which again is another tuple of count and num. Heap replace, behind the scenes, pops off the root of the heap and then adds on this value. So it does a pop and then a push automatically, and it's just a little bit more efficient. Once we do that, we have to do the part at the end where we iterate over everything in the heap and grab these second values and put them all into an array and return that. I'm actually going to use a list comprehension here for simplicity. If this doesn't make sense, let me know in the comments, and I can also write out the way you would do it with a normal loop. But we can just return a list where we take value 1, so the second value of the tuple, for value in heap. So this is basically doing a for loop where we loop over each value in the heap, and remember value is a tuple, and we want to take the second value of the tuple, which is the number associated with the count. So let's see if we have any mistakes here. It looks like that works on our 2 test cases, so we will go ahead and submit. And that looks like it's working. So this is a fun problem where we have to use both a dictionary and, in my case, a heap. There might be other ways that you can do it, but I thought this was a cool way to utilize some tools that we've learned by solving earlier problems in the NeetCode set to solve this one. And if we look at our runtime, okay, it's about as good as we can get. So even though it's 53rd percentile, this is about the fastest you can do it. So thanks so much, and I will see you in the next video.